Alright, the chain rule. So, when we're looking at the chain rule, I want to look at it from a Calc 1 perspective first. So, if you recall, from Calculus 1, we use the chain rule on composite functions. Which, look like this. F composed with g of x equals f at g of x. So we use the chain rule on functions like this when we're doing derivatives. But as you already know, in Calc 1, this is a single variable function. So what if we use the chain rule on functions that have, when the variable that we plug in has two or more variables, and each one of those variables has a set of other variables as well. So when we're using multivariate functions, the chain rule is a little more sophisticated than just using the derivative of this. So let me just make a note here. So note. So the basic idea from single variable functions still apply. However, there are more variables to consider. So, okay. So, how do we consider all these, how do we take into consideration all these different variables? So, the best way to show how the variables are related to each other is by making, and your textbook calls it the same thing that I call it. It's called a dependency diagram. It's also called a dependency picture. So it's by making a dependency picture or diagram. So, as you'll see, it's really not too complicated to understand, but you'll see what I mean from the various examples that we look at. So suppose, let me give you this example here. So suppose I have x, y, z, which is a function of s and t, and that's equal to the function s squared minus t squared, comma s squared plus t squared, comma s times t. And I have the function u and v, which is a function in x, y, and z. And that component-wise is 2xy minus 3yz, comma x times z. So those are my functions. All right. So I have question A. Use the chain rule to find the derivative of so you can see how I'm calling this as a function of f and this is a function of g. So kind of like the same way we'd use composite functions for single variables, I'm going to use it for multivariables as well. So the composite function, so this is the notation of it. We write it as the derivative of f composed with g I'm sorry. Let me switch these around. Sorry about that. It's the derivative of g composed of f. And since f is the inner function, we're going to look at the variables the functions are, s and t. So really what this means is, this is just another way of saying this, but since we're dealing with multi-variables, we're just expressing it differently. So this is still g composed of f, but since f is going into g, so I'm taking this function and I'm plugging it into this function, since this is the inner one and that's the outer one, just like it is up here. So yeah, sorry about that, but I'm going to use the chain rule to find the derivative of this function. All right, so what you're going to do is you're going to draw a dependency diagram. That's all you're going to do. Draw a dependency diagram. So it doesn't matter how you set this up. All you have to do is see how the variables are related to each other. As you can see, g is a function of x, y, and z, and f is a function of s and t. So how did the variables relate? Well, so since I want my variables, since I'm taking the composite function of g and f, or g composed with f, and my variables are going to be s and t, that means my ending variables in my diagram are going to be s and t. So what am I starting off with? Well, if I'm ending here, that means I'm starting here. I'm taking this and I'm plugging it. I'm taking this and I'm plugging it in here. So I have u and v. And what are the variables that u and v are in? X, y, and z. Right? And what are x, y, and z variables of? Well, they're in terms of s and t. So u goes to x, u goes to y, u goes to z, and v goes to x, y, and z as well. Similarly, x is in terms of s and t, y is also in terms of s and t, and z is also in terms of s and t. So that's the dependency diagram. So if you want to take the derivative of f composed with g, this whole diagram represents the derivative of the entire function. That's an important note. Note, the entire diagram represents the derivative of the whole function. What do I mean by that? By the whole, I mean the entire function. If I say take the derivative of this function, I'm saying you're looking at all the branches from u to s, from u to t, and all the branches from v to s and from v to t. All those derivatives, those four branches, or those four different branches paths, will be the derivative of this function. But if I just go to question B, for example, let's say I'm only interested in a particular branch. For example, find the partial of u with respect to s and the partial of v with respect to s. So if you want to do that, so if I want to get du ds, right? So I'm just looking from u, all the branches from u to s. Okay, so what are they? So from u to s, well, here's one branch, here's another branch. Here's this branch to this branch, and then finally u to z, and then from z to s. Those are all the different ways you could traverse from u to s. That'll give you the derivative of u with respect to s, the partial derivative. So now you just multiply, so each branch represents the partial derivatives of du dx. This is dx ds. This branch right here is du dy, and this one right here is dy ds. And then finally, this is du dz, and this is dz ds. So to find the partial derivative of u with respect to s, you just multiply the two derivatives in one single branch and add the product and add all the branches together. So to find du ds, I take this product and this product plus this product and this product and this product and this product. So my final expression for the partial of v with respect to s is du dx times dx ds. And you can see how that works, because if I cancel out the dx's, what do I get? I get du over ds, which is what this is equal to. So you can see how the algebra kind of, it shows you the answer. Plus the product of the second branch, so du dy times dy ds plus du dz times dz ds. That right there is how you get the partial of u with respect to s using the chain rule. Now that's just one particular branch. That's the branch from u to s. I ask you to find dv/ds as well. So if you do that with a similar argument, so if I want to find dv/ds, right? So v to s, so you just go from, so for example, you just go from v to s in all possible branches. So here's one branch. Right? Here's the second branch. And then here's the third branch. Alright, so now just go through the work again and label them all out. So this branch right here is dv/dx times dx/ds. You can see how the dx is canceled and I'm left with dv/ds. Just like here, the dy's cancel, the dz's cancel, with the original term dv/ds in each one. Plus the second branch, dv/dy times dy/ds plus dv/dz times dz/ds. And that's it. But you know, that's how you find the expressions for them. But since I gave you explicit functions, you have to actually find them. So I'm not asking you to find an expression. I'm asking you, all right, compute, you know, the partial of this and the partial of this. Now, if I wanted to, you know, the entire diagram represents the derivative of the whole function. So this is only half of the function, right? This is from u to s and from v to s. The other two pieces would be from v to s and v to t. Right? So these are the two partials. So this goes from u to s and from v to s. The other two would be from u to t and from v to t. Those other two, with these two, would comprise the derivative of the whole function. There's a lot of dv blah blah junk going on here, but it's really not that bad if you just take it one step at a time. So when it comes to actually computing this, you just have to take the derivative. So this is u, not to be confused with v. You just take the derivative of each piece separately. So du/ds, so du with respect to x. Alright, so the derivative of u with respect to x. So how are you going to do that? So the derivative of u with respect to x. So if I take the derivative of this with respect to x, well, this is going to be treated as a constant because it just contains y and z. This is the only term with x in it, so the derivative of x is 1, so I'm going to have a 2y. Right? And the derivative of x here is 1. Well, I'm sorry. So I don't care about this one because u is equal to this, right? This u is equal to that, right? This is what u is equal to. This is what v is equal to. Sorry about that. So since the u is there, you're taking the derivative of this with respect to x. I don't care about this last term. I only care about this term because it contains x. Derivative of x is 1, so I have 2 times y. So this right here is 2y. This right here is 2y. And you're going to multiply that by the derivative of x with respect to s. So x, this is x, and x is equal to s squared minus t squared. So take the derivative of this with respect to s. So that's easy. T squared we ignore. That's a constant squared. S squared, the derivative of S squared is 2S. So you're going to multiply this by 2S. And then just keep going. Plus du dy. So the derivative of u with respect to y. So this is going to be what? 2x minus 3z. And then you're going to multiply that by dy ds. So the derivative of the y with respect to s. So that's just going to be 2s as well, right? Plus, and now the last one. So du dz, right, the derivative of u with respect to z. So there's only one term here with z. That's the first term's a constant. Derivative of that is 0. I don't care about it. The derivative of this is 1, so I'm going to have negative 1. I'm going to have negative 3y times 1, which is negative 3y. And then finally, dz ds. All right, so the derivative of z, so this is z, right, with respect to s. Well, the derivative of s is 1, so 1 times t is t. And that's it. That right there is the derivative of u with respect to s. Now, a similar process, you could do that to get dv ds as well. And just go through it, term by term, just like I did up there. dv dx, dx ds, and so on. So if you do that, so I'll go through it here. So the derivative of v with respect to x. So this is v. So this is what v is equal to, right? V is equal to this. So what's the derivative of v with respect to x? Well, that's going to be 1 times z, which is just z, times the derivative of x with respect to s. Alright, so this is going to be what? That's going to be 2s again, plus the derivative of v with respect to y. So the derivative of v with respect to y. Well, v is equal to xz. So the derivative of v with respect to y doesn't have any y's in it. So this is just a constant. What's the derivative of a constant? 0. Right? And then the derivative of y with respect to s. So y is equal to s squared plus t squared. So the derivative of y with respect to s is going to be 2s again. You could kind of see it. This and this, they're, these two terms are the same in each derivative. It's these terms that change. So yeah, these two terms are going to match. So plus the last one. So dv ds, or I'm sorry, dv dz. So the derivative of v with respect to z, that's going to be x times t, right? Because you can check it yourself. The derivative of z with respect to s, that's going to be 1 times t, which is t. And I'll just leave a note here. Even though we're taking the derivative of these functions with respect to s, right? I'm leaving the derivatives in terms of x, y, z, s, and t. So I'm leaving, if you look at these derivatives, they all have x, y, z, s, and t in them. And since we're taking it with respect to s, if you really need everything, in terms of s, just substitute you could substitute the x, y, and z equations in for s and t. So you can kind of do a little substitution. You could substitute the x, y, and z equations. It's not necessary that you do that, but you know, it will give everything in terms. So if you look here, right, what's x equal to? Well, x is equal to s squared minus t squared. So if I plug that in there, I'll get 2s squared times minus 2t squared, and you know, if I keep going with that, eventually I'll get. You'll boil down all these variables into variables with s and t in them. But again, it's not mandatory, but that's how you would do it. But this is perfectly fine. Let me show another example. And you know, most of these problems, they all have the same flow to them. They're really not much different. Okay. Suppose w is equal to 5x squared times y minus y squared times z plus the natural log of z, and x is equal to cosine of 6t, y is equal to 2 over t plus 3, and z is equal to e to the power t squared. Find dw dt. Sorry, I meant to write a partial here, but I wrote a regular derivative. I got Calc 1 on the brain. Alright, that's just sloppy. That looks good. Alright, so again, if I asked you to find the derivative of this function, like the derivative of this function with respect, like find the derivative of the whole function, you would look at all the branches from your dependent variable to your independent variable. So, you know, just to reference your notes here, right? These variables right here, these are your dependent variables. These are your independent variables, like s and t. Right? These are your independent variables. And the variables in between are called your intermediate variables. I know I'm kind of squeezing that in there, but that's the gist of it. So if I come back here, so if I want to find a particular partial, I have to draw the dependency diagram. So the dependent variable is the function that you're differentiating. So dw, so w is my dependent variable, so I'm starting with w. All right, what's w in terms of? X, y, and z. All right, what are x, y, and z in terms of, if any? Well, you could look, x is in terms of t, y is in terms of t, and z is in terms of t. So you only have one independent variable. So that means x, y, and z are only in terms of t. That's my dependency diagram. That's my independent variable. I'm sorry, this is my dependent variable. This is my independent variable. And these are my intermediate variables. This is dependent. And it's independent. So if I want to find dw dt, well, just find the branch. So if I look at this, well, what are all the branches that go from w to t? It turns out to be the whole diagram, doesn't it? I mean, I could draw them out, but they all end up at the same place. So in this case, since my intermediate variables were in terms of one variable only, my whole dependency diagram is just one particular derivative. So it ends up being the derivative of the whole function. So in this particular case, my whole function's derivative is just this one derivative. And now, you know, it depends on how many intermediate variables you have and how many independent variables you have, but basically making the dependency diagram makes it all make sense. So just follow the whole diagram to t for each branch. So this is partial of w with respect to x times partial of x with t, partial of w with y times partial of y with t, and the partial of w with z times the partial of z with t. So now from here, just take the derivative, find the derivative of each one of these terms and plug them in and you're good. So the partial of w with respect to t is equal to, so alright, what's the derivative of w with respect to x? So, alright, so I only care about x's, everything else is a constant. So this is a constant. So I don't care about this term or this term. I can ignore both of them. So what's the derivative of that with respect to x? So that's going to be what? Use the power rule, right? So the y just sits there. So that's going to be 5 times 2. That's going to be 10x to the first times y. So that's going to be 10xy, right? So dw dx is going to be 10xy. dx dt. Alright, well, x is only in terms of t, so what's the derivative of cosine 6t? Well, the derivative of cosine is negative sine. And since I have a 6t, I'm bringing that 6 out. So this will be negative 6 sine of t. Negative 6 sine of 6t, I should say. Right, you're just using the chain rule there. I mean the single variable chain rule. Alright, plus dw dy. So, alright, well, I don't care about this term. So, the derivative of y here, that's 1. So I'm going to have 5x squared minus the derivative of y squared is 2y. So I'm going to have 2yz here. So I'm going to have 5x squared minus 2yz. Alright, that's the derivative of w with respect to y. Okay, now what's the derivative of y with respect to t? So that's this one. So again, this is 2 over t, so I could write this as 2t to the negative first, right? So if you use the power rule there, you're going to have negative 2t to the negative second. And obviously the derivative of 3 is 0. So this is negative 2 over t squared. Right, and then the last product, so plus, now dw with respect to z. Alright, so I don't care about that. Derivative with respect to z is negative y squared And what's the derivative of natural log of z? That's going to be 1 over z plus 1 over z. All right, that's this product. Then a derivative of z with respect to t. All right, well, how do I take the derivative of z with respect to t? Well, I'm using the chain rule here, right? There's my whole function, and here's the inner function, right? So the whole derivative is, well, the derivative of e to the stuff is just going to be e to the stuff, right? So that's going to be e to the t squared power times, now it's going to be times the derivative of the stuff. What's the derivative of 2 or t squared? That's going to be 2t. And that's that product right there is the derivative of z with respect to t. And since I went through the whole shebang, I went through all the branches, that's the derivative, that's the partial derivative of w with respect to t. And again, if you need everything in terms of t, you could substitute using the x, y, and z equations. It's not necessary, but you can. Just, x is equal to cosine of 6t, so you can replace that here, and y is equal to this, 2 over t plus 3. And, you can go through that and you'll get everything in terms of t, but it's not necessary, only unless it's explicitly mentioned. But if it's not, we could stop there, that's fine. So, when it comes to the chain rule, it really all just depends on the dependency diagram. If the derivative you're looking for is, so the dependent variable is the function that you're differentiating, and the independent variable is obviously this. Think back to Calc 1, right? If I want to take the derivative of this, I'm taking the derivative of, well, Calc 1 we wouldn't use fancy d, we would just use regular d, right? That's the derivative in Calc 1. That's the derivative of f composed of g of x, right? Take the derivative of this function with respect to x. That's the dependent, this is the independent. So same idea here. I'm differentiating u, so u's dependent with respect to s, so s is independent. So when it comes to the chain rule, that's really it. But to end this section, I do want to talk about one more thing. I want to do implicit differentiation. So just like there's implicit differentiation in single variable calculus, there's implicit differentiation for multi-variable functions. The same thing applies to multivariate functions as well. Okay, so this actually really isn't that bad, but it's pretty straightforward. But the basic idea comes from, let's suppose I have a function in terms of x, y, and z, and it's equal to 0. Right? So I have a multivariate function equal to 0. And if I go through the derivation, right? So let's implicitly define a function z is a function of x and y. It doesn't matter if it's 3 variables or 2 variables. It's just a multivariate function. It could be 2, 3 variables or more, whatever, equals 0. So if I define it as z or whatever, where f is differentiable, I'm going to let w equal the three-dimensional case, or three variant case in this particular derivation. Then if I take the derivative, so if I go through this with the derivative, so then the derivative of w with respect to x so if I go through this, I'm using the chain rule here. So the derivative of w with respect to x is going to be, well, it's going to be derivative of f with respect to x, and then it's going to be the derivative of x with respect to x. So don't worry if you don't understand this derivation. I'm just going through the chain rule with this. So then this, using the chain rule, I get df dx times, and then I have the derivative of x with respect to itself, plus the derivative of f with respect to y, times the derivative of y with respect to x, plus the derivative of z, or derivative of f with respect to z, times the derivative of z with respect to x. Alright, so if I go through this and take the derivative of the function, then I take the derivative of each independent variable. Using the chain rule, I get that. Okay. But I want to find a way to find the derivative of this function implicitly. So if I look at this the way I did it, since I'm making this assumption, right, the function is equal to 0, since we have this assumption, right, provided the function is equal to 0, I could say the following. So since this is equal to 0, all right, well then a derivative of this with respect to x, what's the derivative? If I'm saying this is equal to 0, right? If I'm saying this is equal to 0, should be capital F, but if this is equal to 0, then what's the derivative of a 0 with respect to x? Well, what's the derivative of any constant? It's 0. So since this is the case, I could say that dw dx is 0. If I look here, so that's what this is, right? If I'm saying this is equal to 0, that's the assumption I made here at the beginning, and I'm letting w equal this. Well, what's the derivative of 0 with respect to x? 0. Okay. What else do I know? Look at this as well. What's dx over dx? Well, what's anything over itself? It's 1. And then, is anything else equal to 0? Yeah. So dy dx, dy dx is also going to be 0 because hold on one second. Did I say dy dx must be 0? I think I mean df dy should be 0. No, dy dx is also equal to 0. So if I make this assumption and I plug it in here and I solve for this, I could get a formula for the implicit differentiation formula. So what I'm going to get is I'm going to get 0 equals the derivative of f with respect to x times 1, right, plus this quantity is going to be 0 plus df dz and dz dx. So this right here is the function with respect to x, this right here is the function with respect to z, and if I want to find the partial derivative of dz with respect to x, what I could do is I could solve for this. So then when I do that, so if I solve for that, what I get is I get the derivative of z with respect to x equals, and if you, this is just algebra, if you just solve for this here, bring this, subtract this over here and divide it by this, you're going to get negative partial of f with respect to x all over partial of f with respect to z. Or I could write that in a much nicer way. I could use the alternate alternate way to denote the partial derivative. I could write it as minus f sub x all over f sub z. So that's if you want to find the partial derivative. Don't worry about the derivation so much. Just worry that if you have an implicit function like this and you want to find the partial of a dependent variable with respect to x, or if I want to find the partial, and I'll make a note of this later, but if you want to find this, you just need to know this. It's just negative the partial of the function with respect to x divided by the partial of the function with respect to z. So I'll say similarly, I'll add this up here, similarly, you could say the partial of z with respect to y equals negative f sub y all over f sub z. So if you want to find either partial or implicit differentiation, you could use either one of these two formulas. These are the two you need to know. Okay? Again, don't worry about the derivation so much. So if I go to the next page, let's do an example. And then that'll be it for this section. So given the function x times y times z minus 4y squared z squared plus cosine of xy. Now this is cosine of xy. It's not cosine x times y. X and y are being put into cosine. This product is being put into cosine. Equals 0. So suppose that multivariate function defines z as a function of x and y. find the partial of z with respect to x and the partial of z with respect to y. So you could tell that this is an implicit function because it's all a bunch of variables all intertwined together. They're like, you don't have an explicit function like earlier in the notes, right? These, like for this example, these variables were defined explicitly. They were solved for a particular variable. This function is implicitly defined. It's not solved for a particular variable, but since it's equal to 0, in addition, I could use implicit differentiation. So I'm going to let f as a function of x, y, and z be equal to this function. So I have x times y times z minus 4y squared z squared plus cosine xy. So now to find each one of these, you just use your implicit formula, right? So the implicit formulas. So the partial of z with respect to x equals negative the partial of the function with respect to x over the partial of f with respect to z. And the partial of d of z with respect to y equals the negative the function, the partial of the function with respect to y all over the partial of the function with respect to z. So those are the two formulas you could use to find the derivative of it implicitly of an implicit multivariate function. So, all right. So since I'm going to be doing the partial of f with respect to x, y, and z, you might as well compute all of them. And then just take the ratio of those two to get the desired partial derivatives. That's it. All right. So what's f sub x equal to? So take the partial of this with respect to x. So you take the derivative of x, treating y and z as constants. All right. So just take it one term at a time. So y and z are constants here. The derivative of x is just 1, so I'm going to have 1 times y times z. So I'm going to have yz. Well, this doesn't contain x. So this is a constant. What's the derivative of a constant? 0 minus 0 plus. So now I have this is the partial with respect to x. So y is being treated as a constant. Now remember, that's what I have here. So what am I doing here? I'm doing the chain rule, right? I'm treating y as a constant. So that y, this is similar to something like this in Calc 1. Cosine of some constant times a variable, like 3x. That's similar to something like that, right? So to take the derivative of that, you would bring the 3 out and then keep it inside. So in this case, you're bringing the y out and keeping the y inside. So what's the derivative of cosine? Well, the derivative of cosine is negative sine. All right, so you're going to have negative sine of xy. And then the derivative of the inside. What's the derivative of the inside with respect to x? Well, it's going to be 1 times y, so that y comes out. So you're going to have negative sine y with a factor of y outside. So that's it. That's the partial of f with respect to x. So I have yz minus y sine of xy. Okay. So now what's the partial of f with respect to y? So, all right, well, this one, that's going to be xz minus, what's the derivative of this with respect to y? So the derivative of y squared is going to be 2y, so I'm going to have 4 times 2y times z squared, so that's going to be what? That's going to be 8y z squared. Okay, and then, well, this doesn't contain, or I'm sorry, yeah, this does contain a y. So again, it's going to be something like this, except I'm not going to have 3x now. I'm going to have 3y instead. So in this case, it's going to be like this, but instead I'm just reversing the the idea of the variables. So here, x is going to come as a factor, not y. So the derivative of cosine again is negative sine of xy. But since I'm taking with y, I'm differentiating y, and x is coming out as a factor. So I'm going to have minus x outside. So that's the partial with respect to y, that's the partial with respect to x, and then finally partial with respect to z. So this is going to be xy. This will be what? So the derivative of z squared is going to be what? Bring the 2 out, so it's going to be negative 8. What? Negative 8 zy squared. And then the derivative, well, this doesn't contain z, so this is just a constant. So the derivative of that is 0. So then that's it. That's the partial of the function with respect to z. So to get my answers, so therefore, the partial of z with respect to x is going to be negative the function with x. So it's going to be negative of this. So it's going to be negative yz minus y sine xy all over f sub z, which is going to be this. xy minus 8z y squared. Again, if you want to distribute the negative here and make the, if you want to distribute the negative, go ahead and knock yourself out, but it's really not that bad. It's really not important. And then the other partial, negative f sub y, so it's negative of this, all over f sub z, which is this. And that's it. It really looks ugly, but it's really not that bad. So that's how you find the partial derivatives of implicitly defined multivariate functions. And it's really not that bad, but again, when it comes to doing partial derivatives, you're just really applying the rules that you learned in Calc 1 and treating the other variables as constants. But other than that, it's really not that bad in my opinion. So, alright, so in the next video, or in the next 2 sections, I'm going to talk about directional derivatives and gradient vectors. And then we're going to start talking about tangent planes. How do you find a tangent plane of a given surface? Yeah, and we're going to be looking at stuff like that. So, when we look at when we look at directional derivatives, we're going to start looking at a new kind of operator, which is called the gradient vector, or we call it the del operator. And that may or may not seem familiar to you, but that's what we'll see in the next section when we look at that.